All right, let's talk about a term you hear thrown around all the time in the news, but maybe you're not 100% sure what it means. I'm talking about uranium enrichment. Yeah, that phrase, right? It's always popping up when people talk about energy, or weapons, or international relations. So in this explainer, we're going to break it all down. What is it? How does it actually work? And most importantly, why is it such a big deal? You'll see that understanding this one concept is key to unlocking a huge piece of global politics. Okay, so to really get to the bottom of this, we have to think small, like really small. We're talking about zooming all the way in, right down to the atomic level. So say hello to uranium. It's element 92 on the periodic table, a fundamental building block of our universe. I mean, this thing has 92 protons crammed into its core. And get this, as far as we know, it's the heaviest element that you can just find laying around in nature. But, of course, we humans weren't just happy with what the universe gave us, were we? Nope. In our labs, we've gone and created even heavier elements. We've literally pushed the periodic table all the way up to element 118. Pretty wild, right? Okay, so here's where it gets really interesting. When you dig up uranium ore, it's not all the same stuff. It's actually a mix. The vast majority of it, like 99.3%, is this stuff called uranium-238. But then there's this tiny little sliver, less than 1%, of something called uranium-235. And trust me, that tiny little fraction, well, it changes everything. These different flavors of uranium, they have a name. They're called isotopes. Now, they're all still uranium. They've all got those 92 protons. The only difference is the number of neutrons, which just means they weigh slightly different amounts. You can kind of think of them like siblings. You know, they're from the same family, but they're not identical twins. So that begs the question, right? What is so special about that tiny 0.7%? What makes uranium-235 the star of the show? Well, it has this one amazing, remarkable property that its much more common sibling, U-238, just doesn't have. Okay, check this out. It works like this. You take a neutron and you fire it at a U-235 atom. Bam! The atom splits apart. That's called fission. And it releases a burst of energy. But that's not even the coolest part. The real magic trick is that when it splits, it also kicks out 2 or 3 brand new neutrons. And what do those do? Well, they fly off and hit more U-235 atoms, which split and release more neutrons, and on it goes. It's this incredible cascade, a self-sustaining chain reaction. So where's all that energy coming from? It seems to come from nowhere. Well, if you could somehow weigh all the pieces after the atom splits, you'd find they weigh just a tiny bit less than the original atom. That little bit of missing mass hasn't disappeared. It's been converted directly into a huge amount of energy, just like Einstein told us it would with his famous equation E = mc squared. And this is the absolute key to everything. Only U-235 can kick off that incredible, self-sustaining cascade of energy. If you hit the other isotopes, like U-238 with a neutron, sure, they might split and release a little energy, but they don't release those extra neutrons you need to keep the party going. And if you don't have a chain reaction, you don't get nuclear power, and you definitely don't get a bomb. So this all leads us to one gigantic engineering problem. I mean, how on earth do you separate the rare, super useful U-235 from the much more common U-238, especially when they're all mixed up together at the atomic level? See, that's the real challenge. Chemically speaking, they are identical. They act the same, they look the same. The only difference between them is a ridiculously small change in weight. We're talking about just 3 tiny neutrons. It's like trying to sort a giant pile of sand where almost all the grains are exactly the same, but a tiny fraction are just imperceptibly lighter. How do you even begin to do that? Well, the solution is frankly as brilliant as it is mind-bogglingly difficult. What you do is you take solid uranium, you turn it into a gas. Yep, a gas. And then you spin that gas at just unimaginable speeds inside this machine called a centrifuge. Because the U-238 atoms are just a teensy bit heavier, they get flung a little further to the outside. That allows you to ever so carefully siphon off the slightly lighter, more valuable U-235 from the middle. It's an incredible process. All right, so now you've figured out how to start separating these isotopes. What can you actually do with them? Well, it turns out that everything, and I mean everything, depends on the purity. It's all about how much of that special U-235 you've managed to collect and concentrate. Yeah, the level of purity or enrichment totally dictates what you can do with it. Check this out. If you enrich the uranium so that it's about 5% U-235, that's perfect for a nuclear power plant to generate electricity. If you push that enrichment level up to around 20% or so, now you've got fuel that can power a nuclear submarine for decades without refueling. But, and this is the big one, to create a nuclear weapon, you've got to purify it all the way up to over 90% U-235. So you can see, the level of enrichment is absolutely everything. So it's pretty clear that this whole centrifuge technology is the absolute key to the entire process, right? It's the thing that unlocks the power of the atom. But how can we really wrap our heads around a concept that's this complex? Believe it or not, you actually see a super slow motion version of this principle all the time. Just think about Italian salad dressing. When you let it sit, what happens? Earth's gravity, which is basically a very slow 1G centrifuge, pulls the denser vinegar down to the bottom, and the lighter oil floats right up to the top. It's just separation by density. Right, but separating oil and vinegar is one thing. To separate uranium atoms, where the weight difference is almost nothing, you need a force that is just exponentially more powerful. We're talking about machines that spin so incredibly fast, they generate forces approaching 1 million times the gravity of Earth. 1 million Gs. Just think about that. That's the mind-blowing level of power and precision engineering you need just to tell the difference between two atoms that are only separated by 3 measly neutrons. So who would have thought, right? A concept as simple as a centrifuge could hold so much influence over the balance of geopolitical power. The next time you hear that phrase, uranium enrichment, in the news, you'll know exactly what they're talking about. It all comes down to this incredible scientific process, using immense physical forces to sort atoms one by one. And that is how a simple spinning machine becomes an object of immense global power, capable of either lighting up an entire city or holding the world hostage.